So good morning, everybody. It's my pleasure to introduce this first pre-seminar of the spring quarter. And it's even more a pleasure to introduce our speaker, who's Raudel Avila. Raudel is a PhD candidate in mechanical engineering at Northwestern University. He's working on his doctoral degree under the supervision of Professor Yonggang Wang. He has a Bachelor of Science in Mechanical Engineering from the University of Texas at El Paso, and he's currently supported by a National Science Foundation fellowship and a Ford Foundation fellowship too. His research deals with the mechanics of electromagnetics in biointegrated electronics for health monitoring applications. And thank you so much for giving this talk. You can start whenever you're ready.
Okay, thank you so much for the introduction. Let me just. Yeah, thank you so much for the introduction, and I'm very happy to present my work. Today I will be talking about modeling programmable drug delivery in bioelectronics with electrochemical actuation, and this is part of my PhD research in Professor Huang's group. So let's start. Some of you may be familiar and probably have used one or multiple drug delivery systems already. And the examples range from pain relief pills, like this one right here, all the way to asthma inhalers. And the delivery approach can be divided in two categories. One is systemic delivery, that is affecting the entire body, or targeted delivery, which are specifically intended to go directly into the region affected. In case, like, for example, for allergies, when we have some congestion, we can use nasal spray to kind of clear the nasal area, and similarly the inhaler for people that have asthma to clear the respiratory the airway so that it's easier to breathe. Now, targeted delivery, it's an area of interest in targeted delivery is cancer therapeutics because of the severe side effects associated with cancer therapy or cancer treatment. So for example, if we focus on brain cancer, an approach to target the brain directly might be biodegradable implants. However, this approach has some challenges that one, it requires a surgical approach. Therefore, there might be some poor penetration in the areas of the brain. And depending on the stage of the cancer, the invasiveness of the tumor cells might be too broad. So it might not be specifically located at one region, so you might have multiple regions in the brain that are affected. So a single device or a single approach is not going to be very useful in that case because you cannot have very large, flow rates or very large distribution in the brain. You need to consider how fragile this organ is, and the drugs generally have low diffusion to try to do the therapeutics. In the context of skin cancer, you can think of it as using topical creams directly into the affected zone. So in this case, you will directly apply the cream into the affected zone and then to treat it. However, one of the challenges is that you're trying to minimize systemic absorption through the skin layers that will eventually end up affecting other parts of your body. So targeted delivery, it's a nice way or nice approach that scientists, engineers, and clinicians are looking at to try to minimize the side effects in unwanted regions of the body. Now, in the context of bioelectronics for targeted delivery, we can think of different examples. Here we have a headset that's intended to do neural recordings on a mouse's brain. So it's directly implanted in the mouse's head, and it has a rechargeable battery. And another example is these microprobes that are intended to deliver fluids into the mouse's brain. However, this approach, you require external connections like an electrical connector to supply power, and this tubing that connects to reservoirs outside to supply the drug. And you will end up implanting these microprobes into the brain and then provide stimulation. So some of the challenges with that is that wired implants will restrict the animal movement. Then battery operated devices will potentially need to be recharged. And if the battery runs out, then you need to replace it. And some of them only include single stimulation. That means that you can only do one experiment at a time, whether it is electrical stimulation or light stimulation or drug stimulation. And in the context of neuroscience or behavioral neuroscience, the ability to combine experiments represents a huge advancement so that researchers can have kind of like a kit to do their experiment with a single device. Some of them are one-time use, that is that you cannot refill them for repeated experiments. And the focus of my talk will be on the precise volume and flow rate control. That is how to make sure that we're delivering the drug at the required time frame and with the required or necessary flow rates to not damage sensitive areas in the animal. Now, as part of our group in collaboration with Professor Rogers in 2019, there was a device that was that combined pharmacology and optogenetics. That means drug stimulation and light stimulation in a single device. So this device, it's implanted on top of the brain. It's a brain phantom for illustration purposes. And we can see that you have your powering an indication here that the device is working and it's wireless, and you have light and drug stimulation. Then similarly, we have another device intended for another location. That's the peripheral nerves. This one will be located in the backside of the animal, and then through a series of microchannels and electrical connectors, it would be placed on the nerve directly to provide a kind of stimulation. So the advantages are you achieve unrestricted animal movement so that your analysis is not affected by the device itself. It's wireless. You don't need a battery to power it. And I will talk a little bit more about this in the next slides. And you can combine types of stimulation. That is, you have drug and light stimulation, and it's refillable. Now, it's interesting to think of these devices in the context of animals. However, what if we think about humans, or how can we adapt this to humans and how to use them, for what purpose, and what sensors are they going to be incorporated? So we can kind of think about, hey, can we use this kind of technology for humans? So at this point, I would just leave that there in your mind to see, hey, how do we go from designing this for animals and then maybe adapting it to humans? But first, let's understand how these devices work. So what makes it wireless? The mouse, here's our mouse on a cage. The mouse moves freely inside the cage that's wrapped with an antenna. This antenna generates a magnetic field inside the cage. And then if we zoom in into our mouse, we can see that there is a coil. This coil harvests the energy generated from the magnetic field. And it uses the energy to power electronic sensors, in this case, to power the electronics for light stimulation, and also the pumping system that's to deliver or push the drug out of the device into the animal's intended region, in this case, the brain. So this approach serves to make rid of the batteries. We can generate a magnetic field inside the cage and then use our electronic sensors or coils to harvest that energy. Now, let's look at what the device looks like and some of the subsystems involved in this bioelectronic. So we have the coil antenna, then we have a set of electrodes here that are placed below micropump refilling ports where a chemical reaction takes place, and then that forms a flexible membrane that pushes the drug from the drug refilling ports through a network of microchannels into the desired region. So this is the device intended for the nerves. Now, we can look at a more simplified schematic where we can see that we have our electrodes here in yellow, where there's an electrical current supplied to them. And we have our electrolyte chamber where the electrolysis or chemical reaction takes place to increase the pressure, and that forms the membrane shown in purple, to push the drug in pink through the network of microchannels. So it's important to note that The system has two chambers, one for the electrolyte and one for the drug, separated by the membrane, and the drug chamber can be designed accordingly depending on the type of volume, on the volume of the drug that we're trying to deliver. In this case, for the device published in 2019 was about 1.5 microliters. So gas formation from the electrolysis, you'll generate oxygen gas and hydrogen gas. So the theoretical gas generation rate is going to be given by this term, N dot. That's 3I for the electrical current over 4F, where F is the Faraday's constant. So we can consider the electrolysis part by this term, where we can see how the bubble formation will end up deforming the membrane and then pushing the drug out through the microchannels into the target region. So this is how our device is delivering the drug. Now, in behavioral neuroscience, we require precise volume and flow rate control to ensure, one, timely delivery and successful delivery, but also minimizing potential damage to fragile surrounding tissues. That is, if you're dealing with a organ like the brain, where you cannot have very high tissue because you will end up damaging the fragile tissues. So our objective is, how do we control this volume and flow rate delivery, and how do we optimize the device for the required applications? And we can do some modeling. So in terms of modeling, we can use numerical models, but they involve many parameters to predict the volume and the flow rate. And we can use finite elements. However, if we start to look at how do we optimize, or how many models we have to run, if we change some of the parameters, we end up doing laborious finite elements just to account for the membrane or the flexible membrane mechanics. So I'm going to use this label as a computer to note in the presentation where we have to use our computer to solve this problem, to use a numerical model. So our goal is to find a scaling law of the delivery. How does these parameters act together and find a solution for the delivery, and find the analytical solution for volume and flow rate without having to use a numerical approach. So I will focus on these two first, and I will use the calculator to denote that we can solve those equations just by using like a graphing calculator. So let's first look at what parameters we have to consider. There are at least 12, ranging from geometrical, flexural, fluidic parameters, going from the environment, microchannel geometry and length, the drug viscosity, the membrane geometry, the membrane materials, gas formation, the coil antenna. So I'm interested not in what these parameters do individually, but how they act together, and how acting together, we can predict the flow rate and the volume. So let's take a look at the solids part first. This is a membrane. So this is a picture by one of our experimental collaborators in Rogers' group. This is a membrane that deforms in the shape of a spherical cap when the pressure inside the electrolyte reservoir increases. And this volume-induced deformation, it's generated because of this net pressure, and the membrane deforms according to a function, this function FB, that depends on the modulus of the membrane and the stress strain curve of the membrane. So we will call this function FB. And this function has to be determined from finite elements. So we have a computer here. We have to use finite elements to determine this function. Now, if we consider the fluids part, the microchannels, there is a pressure difference between the drug reservoir and the environment. That's approximately given by the formula right here, where that has drug viscosity terms, the length of the microchannel, and this one specifically is for a rectangular cross-section. So we can account the resistance from the microchannel based on this formula. So we can start to take a look at our scaling law. And we can do that by obtaining the pressure based from equilibrium in our system, and then use it on the ideal gas law. First, we look at the pressure from equilibrium, and we have three terms. We will just assume that we have a square cross-section, so we can obtain the fluidic term from the microchannels as this 32, and then the drug viscosity, the length of the microchannel, and the cross-section. Then we have the environmental pressure, and we have our function FB from the membrane. Now, we're going to use the ideal gas law because of the chemical reaction taking place on the electrolyte chambers, but we will use the rate form to introduce or to use our gas formation term, N dot, that was this ratio 3/4 IF coming from the electrolysis. So if we just plug in our P here and take the derivative of P, it's P dot, we will find out that we end up with an equation that looks like this. So this equation, it must be solved numerically with the initial conditions B equals to 0 and B dot equals to 0 at time 0. But we don't really want to do that. We're looking for a scaling law. We're looking for analytical solutions. So what can we do? So this equation has many parameters. We have the viscosity, the length, microchannel cross-sections, the membrane mechanics, and the electrolysis. So there are going to be three types of solutions that we can obtain. First, the numerical. We know that we have to use the numerical method, and we have to solve for our function FB from FEA. Now, a semi-analytical solution, we can use singular perturbation method to solve our equation, but still we have to use finite elements to solve for our function FB. And lastly, a full analytical model, where we use singular perturbation to solve our ODE, and we use membrane theory to determine the function FB from mechanics. So how do we do that? First, let's look at our time, volume, and pressure volume curves, and how do we normalize them? We can introduce a time. It's going to be at normalized time, T star. That is the time multiplied by this coefficient that has a current, a constant, temperature, another constant, radius of the membrane, modulus, and the membrane thickness. And this term has units of 1/time together. So this will give the normalization of time. Then the volume can be normalized by the radius of the membrane Q. And our non-dimensional function for the membrane is going to be normalized by the radius of the membrane over the modulus times the thickness. So we have our three non-dimensional variables in the problem. Then we can rewrite our ODE in terms of, and only involves three non-dimensional parameters. Only three. We had 12 before. Now we have three, which is the initial volume, the microfluidic resistance, and the initial environmental pressure. So once again, we have the microfluidic resistance. We're going to call this M star. This term groups the viscosity, the length of the microchannels, the current, the constant from ideal gas law, temperature, radius of the membrane to square, modulus of the membrane square, thickness of the membrane square, Paradise constant, and the microfluidic cross-section. We have our initial gas volume normalized by the radius of the membrane cube, and our initial environmental pressure normalized by the modulus of the membrane and thickness and the ratio between the radius and the thickness. So we have only three non-dimensional parameters that are acting together instead of separately, like in our numerical equation where we had all the parameters spread out. So this way we can find only three parameters for the drug delivery process. So in this case, V star, which combines all 12 parameters from geometry, flexural, fluidic, electrical, all and the environmental terms. So let's look at how is this relevant in terms of experiments. Now, in the experiments reported in the paper for the device in the peripheral nerves, the M star term, when we calculate it, is negligibly small. What does this mean? It's negligibly small as compared to the other two terms, to the other two non-dimensional terms. And this is important. It doesn't have to be small. It has to be small as compared to the other two terms in order to make this, in order to neglect it. Therefore, we can neglect the microfluidic resistance, and we take with it this derivative term. So we can arrange these terms to find an equation, an analytical solution for the drug delivery time, T star, for any given volume, B star. So we have our T star and our V star terms here. And this is an algebraic equation. It doesn't have any derivative terms. And we can just rewrite it in terms of, in its dimensional form. after before normalizing it. But still, we have this computer here. So this computer, it's because of this function fb that we have to calculate using finite elements. But let's take a look at this equation more closely. So this equation has terms from the environment, the membrane geometry, the membrane material, gas formation, and the coil antenna. And we have to solve it from finite elements because we have to solve it, we have to obtain this function fb from finite elements. However, we can still make some recommendations for our experimental collaborators. We know that since we neglected m star, the term, this solution is independent of the properties of the drug and the microfluidic channel. Now, it's inversely proportional to the current and the temperature. It's linear, but not linearly proportional to the initial initial volume and initial pressure. And the time to deliver the drug decreases as the modulus and the thickness decrease, or vice versa if we increase the radius. So if we're looking for fast delivery, that is, we have an experiment where we have a constraint that the delivery has to happen very fast or fast, then we can start to modify the parameters accordingly based on this equation, where we can decrease volume, pressure, modulus, and thickness, or increase current, temperature, and the radius of the membrane. Now, when the case where m star or the flow resistance is small, but not negligible, that means we want to account for the microfluidic resistance, we can solve the equation, the ordinary differential equation, using singular perturbation method. And we obtain a term of the following form, where we have the microfluidic resistance and we have a V bar star term. Now, the first term of the solution, we already solved for it. It was our solution without the flow resistance. Then, using singular perturbation, we obtain this term right here. Now, this term looks very populated and we have many parameters, but in reality, all of these parameters are known, and we have our time variable here in the exponent. We have an exponential decaying term. So this term decays exponentially with time, and we're able to account for the microfluidic resistance. However, we're making the assumption for singular perturbation that this parameter m star is small. Now, let's see how that solution works in terms of how small can that parameter be. So here we're going to look at the volume temporal profile. That is the volume solution over time. Now, this is a normalized time versus normalized volume. And we're comparing our numerical solution with our semi-analytical solution. The numerical, because we have a finite element solution here, and semi-analytical, because we have singular perturbation equation. Now, for m star, when it's 10 to the minus 4 and 10 to the minus 3, we can see that the solution agrees fairly well. Agrees very well in this range. But when we increase m star to about 10 to the minus 2, our assumption on singular perturbation was that m star was small. But if we compare it to our other two non-dimensional parameters, m star is no longer negligible. That's why we have a deviation between the numerical and the semi-analytical solutions. Now, it's also important to have additional equations where we can calculate our lower bounds and our upper bound solutions for the volume. And we don't have to solve the ODE. For this reason, we can calculate lower bound solutions. Our lower bound for the volume, for the delivery time, is going to be when m star is equal to 0. That is neglecting microfluidic resistance, which is just given by our previous equation, by our previous equation of this form. And the upper bound is going to be given by replacing the V star, in this case, V star in this equation. So here, here, and here by this term. So we have the V star plus the first term of the exponential decaying term. So this is an overestimation of the drug delivery time. So these are important because we can solve them without having to use the ODE. Now, I mentioned in the past that the maximum flow rate was an important quantity to control because you can potentially have some damages if you have excessively high flow rates. So we will define the maximum flow rate as the peak value here in our volume, in our flow rate temporal profile, where our solution is going to increase from 0, reach a maximum, and then eventually will just decrease. And we can see that the agreement follows the same pattern that with the volume solution, where our m star, when it's 10 to the -2, the green curve deviates from our solutions. And we can calculate the upper bound for the maximum flow rate. In this solution, you don't need to use numerical methods. You can just simply use your calculator to obtain this value, because all these parameters, you know them from the experiments. So this is a good check to see where you are in your experiments and in your solution. Now let's compare with some of the experiments. So first, the experiments for the device in the mouse's brain. We can see that when they vary the effective current from 0.1 milliamps to about 0.6 milliamps, you achieve different maximum flow rates. So this is a dimensional quantity, microliters per minute. And we can see that our numerical solution, it's slightly above, it agrees very well in this range for low currents, and it slightly overpredicts the flow rate in this area. And we can just use our upper bound solution derived previously and just obtain the linear relationship with the effective current. Now for the flow rate temporal profile, that is the flow rate over time, we can see from experiments how both our upper bound numerical and semi-analytical agree well for the maximum flow rate, which is the quantity that we're interested in. How the solution eventually reaches the maximum flow rate, and then from the delivery, it will just start, the flow rate will just start decreasing until the delivery is complete. Now, here we talked about the scaling law and also the analytical solutions for volume and flow rate. But now we still have to use finite elements to obtain the FB curve. So we're looking at how to use membrane mechanics to obtain this FB curve based on the deformation of the membrane. So I will talk about that next in the following slides. So for a linear elastic material, the membrane it's on an equibiaxial state of stress. It's a large deformation. So the membrane will deform following the volume of a spherical cap. And it's like following this volume shown here. And we're assuming that the material is linear elastic. Now, this assumption is for the material model, not for the type of deformation. However, the material model for linear elastic might not be the most realistic because we're dealing with large deformation. So we can use some general hyperelastic theories like Mooney-Rivlin, and we can write our stress in terms of the lambda or the stretches in the following way for the equibiaxial deformation. And following these, we can find the membrane deformation based on the state of stress, depending on the type of material model that we use. Now, it's important to note that a general hyperelastic material model might not accurately reproduce the stress strain curve of your material. So we can use the Marlowe hyperelastic model that's based off the uniaxial stress strain curve of your material. So in this case, our membrane, it's a copolymer, and it's the abbreviation is SVS. And we can obtain the uniaxial stress strain data from experiments, and the Marlowe model will just accurately reproduce that data. So the model is going to be built of that data. So there's no novelty here that they agree very well. So this is what we wanted, because in another case, we might not be able to, a general hyperelastic model might not be reproducing our stress strain data correctly. So let's look at what's happening during deformation. This is our experimental images, how the membrane deforms over time when the electrochemical reaction is taking place. So for the linear elastic material assumption, we're going to use the stress is related to the strain by the equibiaxial stiffness. And we need to find relationships through an intermediate parameter. This intermediate parameter is going to be this angle phi. The angle phi is the angle that tracks the deformation of the membrane in the spherical cap. So as the membrane increase, this angle will serve as like an intermediary to find the relationships for pressure and volume. So first, we can find the relationship between the strain and this angle phi. So here is just kind of like the list and the geometrical analysis. And I'm not going to go into detail on how to do that, but if you have more questions, I'm happy to find them. But I'm happy to discuss them. But the idea is to relate our parameters to this intermediate angle. So we can find our stress in terms of that intermediate angle phi. And we can find our relationship for the pressure in terms of that angle phi. So this will be the pressure obtained from equilibrium for finite deformation. And we can see that we have that relationship for the angle phi right here. And similarly, we can find the volume in terms of phi. So that way, we have our pressure in terms of phi and our volume in terms of phi. And we can combine these equations and get rid of this intermediate angle to find this intermediate parameter to find the relationship for stretching dominated deformation for a linear elastic material model assumption, which is given by this equation here. Or if we just normalize it, it becomes even a simpler equation, just 128 over 3 pi cube, and the volume, it's to the cube. It's a cube. And we can see the comparison between finite elements and the membrane solution. So the finite elements, at some point, is going to find some difficulties predicting the deformation because you're just using the deformation becomes very large. So that material model is not going to be very useful. However, the analysis for the derivation and the geometry, it's still the same. It's still valid. So we can translate that into our hyperelastic models. But we can find it in terms of parametric equations. So previously, I showed the equation for the equibiaxial state of stress for the Mooney-Rivlin, and our FB curve is given by this equation right here. Now, this equation looks very long and tedious, but the only parameter that we're tracking or that we have to solve for is this angle. All the other parameters are known. So we can track the angle phi during deformation, and the volume derived from the spherical cap geometry also just has this angle phi that it's the one we're tracking. So we can combine these two equations and find our FV function. In this case, this is the normalized function for finite elements and our membrane solution. So you can see that they agree very well. And in this case, we don't have to run finite elements. We can just use our parametric equations and obtain that FV function as we just input the angle phi. And for the Marlowe model, that is for our specific type of polymer with our specific stress strain curve, we can find the FB function that's given by this equation right here. And we have the stress given also in terms of phi. So the stress is going to be given by this equation here, and we can solve it, plug the stress into this equation. We have our FB function, and then the volume is still the same. This one doesn't have any material. It's independent of the material model, so it's still valid for the Marlowe model, as well as the Mooney-Rivlin. And we can plot our finite elements and our membrane solution for different values, for different volumes. We can see that for our finite elements and our membrane solution, they agree very well. And this is done just based on the stress strain curve of the material. Now we can compare our volume and flow rate solutions. But the numerical model that's solving the ODE, running finite elements, and our full analytical model for Marlowe, that is, we use a singular perturbation solution where we consider small microfluidic pressure, a small microfluidic resistance, and we use membrane theory to derive the membrane mechanics based on our type of polymer. And we can see that our volume temporal profile agrees very well for the deformation. And we can see that here I have a point, I have an arrow pointing for large deformation where it's a stretching dominated. And we can see that the volume curve also agrees very well for between our numerical solution and our full analytical solution. And you just have to keep in mind that the analytical solution can be solved in minutes or less than minutes to obtain the solution. And then the numerical, we have to run the finite elements and solve the ODE. So this will give us a lot of design space to just tune our parameters depending on the applications. Now, in the past, I told you about future applications. At the beginning of the presentation, I told you how do we use this for humans? How is it relevant for humans? So one of the future applications that Professor Rogers and his team are working on are helping battle the opioid epidemic. So this idea was proposed because, as you can see, in the past 20 years, the number of deaths associated with opioids has risen by a factor of 5. So it's about 50,000 deaths per year. That's about 1/10 of the coronavirus deaths just this past year. This is clearly a health crisis in the United States. Now, their proposed solution, engineering solution control, is how do we use this device that will be equipped with some life-saving medication, in this case, a drug that can reverse the effects of an overdose, by constantly monitoring, in this case will be oxygen levels in a human. And then once the device senses that the human has, or the oxygen levels in the human have dropped, then the device will start, initiate the electrochemical reaction, push the drug through the network of microchannels, deliver the drug to potentially save someone's life, because it will be the case where someone might overdose and they're probably alone, so they're not going to be able to administer the life-saving medication. So this is a way or a proposal to incorporate this kind of technology to help battle the opioid epidemic. Now, it's interesting to note that in small animals or large animal experiments and humans, you're going to have different types of considerations. One of them is what's the volume of drug required? You might be talking about nanoliters or a few microliters, hundreds of microliters volume for the drug. So your device will increase in size. And how important is the time? That is, is this a life-saving medication that needs to be delivered instantaneously or instantaneous stimulation? Or does the time scale of the experiment takes probably minutes or hours? And how important is the flow rate control? So if it's in a very, very fragile region, then you have to consider that you cannot be delivering a very fast flow rates. And of course, where is the target region located? And this is mainly for you want your device to be close to the area of interest, because you don't want to be wired all up through your body. So the way to do that, it's with the term that we've been considering or neglecting or analyzing and solving for, our microfluidic resistance. And we can see that for small animals, we can use the non-negligible flow resistance solution, where we have our first term that neglects the resistance, and then our second term that accounts for the microfluidic resistance. Mainly because in this term, the cross-section, it's in the denominator, and it's to the 4th power. So typical ranges of the microchannel design might be from 10 to 30 microns. So this device, this M star is going to be probably 10 to the -3, 10 to the -4 a range. So you might be able to, you will have to consider it in your solution. But in the case of larger animals or humans, maybe you don't really want to deal with the microfluidic resistance. So you can make your channels larger. Therefore, when this dimension will go into the denominator to the 4th power, your M star is going to be affected by several factors compared to, like just increasing a factor here will have a large impact because it's in the denominator, and you might be able to neglect your m star and just be able to use the simple equation here. We have your time, and then your volume, and then if you determine the function FB from memory mechanics, then you have your full analytical model that you can use to predict the time required to deliver, in this case, life-saving medication or some type of medication. Now, in conclusion, what we've done is show that we have an analytical model that accounts for the effects of the flexible membrane and the microfluidic channels that are embedded in the bioelectronic. And we find that the scaling law depends on 3 non-dimensional parameters. One is the initial volume, B0 star, the initial environmental pressure, P0 star, and the microfluidic resistance, M star. And we found the analytical solutions for any material model and the flexible membrane from membrane theory. So we derived the membrane mechanics depending on the type of material that we have. And just to recap, we shown that we have a numerical solution, and then our semi-analytical solution where we still have to use our computer or use some sort of numerical solver. And our goal is to use full analytical solution that we can solve in faster, and can help us predict volume and flow rate and optimize the device faster compared to these 2 cases. With that, I just want to acknowledge part of my collaborators, both in the theory and simulation part and the experiments part. So Professor Huang, Chen-Han Li, and Yeguang Xue, and in the experiment side, Professor Rogers, Yixing Wu, Abraham Vasquez Guardado, Joanna Ciati, and Jiamin Sang, and funding part of the NSF Research Fellowship and the Ford Foundation Research Fellowship. And with that, I'm happy to take any questions that you have in regards to this presentation, and I hope you enjoy the presentation.
Thank you so much. Thank you so much. Fantastic presentation. So questions from the audience are welcome, from students or faculty attending. So maybe I'll start. Perhaps you mentioned it already, but I liked how by turning on or off some terms into your starting equation, you were able to obtain an upper bound and a lower bound. Are these only approximations, or are to be intended simply as approximation of the exact? So are they the theoretical upper solution you get, upper limit and lower limit, or they are more like an overestimation or underestimation of the exact? Maybe you mentioned it already, but if you can go over the details.
Yeah. So so this will be the upper bound solution for the maximum flow rate. So this solution, here we can see that we have a numerical solution where our maximum flow rate just drops as we increase our M star term. And our upper bound solution, it's kind of just a simple way, or a closed form equation that we can use to predict the volume. Now, we have to keep in mind that if we're working with M stars that are large, then our upper bound solution is not very useful at all. We have a very, very large disagreement. But if our M star is very small, then our upper bound solution, it's going to be very useful to predict the flow rate. Because this upper bound, it's calculated when neglecting the microfluidic channel, neglecting the microfluidic resistance. Therefore, this one has kind of like a range where it can be used. And in terms of the volume, or the volume delivery, the time delivery, we can look at our upper bound and our upper bound estimate for the time, where these ones are, in this case, you don't have to solve the ODE, you don't have to solve the singular perturbation solution. You can just approximate it by looking at the upper bounds and lower bounds. Now here, the black curve, this is the lower bound, neglecting microfluidic resistance. So this is going to be the lowest curve on the graph. Then as we increase M star to, let's say, 10 to the minus 4, then we can find that the lower bound and the semi-analytical solution are very similar. very, very similar. So you don't really have to use your semi-analytical solution from singular perturbation. You can use the lower bound. But if you start to go to 10 to the -3, say this solid curve, then your semi-analytical and your upper bound start to deviate slightly more. So in this case, it will be like a good approximation. But when it's 10 to the -2, then you're kind of like completely off here because your singular perturbation assumption, it's no longer, this value, it's already too large for that assumption.
Perfect, thank you. Other questions? So I may have a little curiosity. You mentioned towards the end extension or extrapolation to other applications and subjects and how it scales, let's say, with the subject, with the patient. In all of and if I understood correctly, it's very much the role of the microfluidics and the size of the channel, the cross section of the channel that matters, right? I wonder if there is anything in the equation that speaks of the delivery environment, let's say the pressure, porosity, fluid content, or if it enters only as an environment pressure that affects the gradient of delivery.
Yeah, well, I think in the environment, or the only term that comes into play from the environment, it's this term. So it will be the initial environmental pressure.
So it's like an environment at fixed pressure.
Yeah, but other than that, we don't really go into much detail in terms of properties affecting the environment, because different organs might have different initial pressures. So it kind of just groups into that part. But we just consider the environment from this singular initial pressure.
Yeah, I understand. I mean, it becomes a boundary condition, basically, other than a system with its own, internal mechanics and hydromechanics. I understand. All right.
Yes.
Thank you. So I welcome other questions. I don't see any hand, virtual or real, being raised. Feel free to unmute yourself and ask questions if you have. Oh, okay, Raul, please go ahead.
So I was observing the M star like value parameter. If there is any small size where you don't have like flow of the fluid of the tube, like when you're doing the design, it should be like very small size tubes of the delivery will not be having flow due to the large M star, or?
Yeah. So let me. Yeah, that's a very good question. So the issue when M star becomes very large is that, like here. So this graph, we're looking at the maximum flow rate versus the M star. So if you reduce the size of your microchannels, let's say 10 micrometers, you might be, in the case of the experiments in publications that I presented, M star, it's around here, but and the fluid flow it will probably be restricted because you will end up with additional challenges associated with that, because the microfluidic resistance is going to be very, very large, and you will end up kind of like blocking your device from that. So ideally, a recommendation for when fabricating the device would be, how do we keep this M star term not here? And the way to do that is, okay, it's how do we change, here. How do we change this term so we have a fixed drug? We can change the length of the microchannel, we can change the cross-section of the microchannel, we can change the current, We can change the radius of the membrane. So we can play with these parameters. And we have to keep in mind that it's not just a single parameter that matters, it's how do they act together. So in this case, if we're just going to change one, the cross section, which might be kind of like intuitive to do just from the fabrication standpoint, which can you use different channels, then we will fix all others and then just change this one because this has the largest influence because it's in the denominator. So the design, I guess, recommendation might be to just keep it when possible in that range to use our solutions. Now, if for whatever reason, impossible, we cannot change it, we have to use M star the way it is, then we can just solve our numerical equation. We still have that, and we can just kind of like go that way.
Thank you.
Yeah, no problem.
All right. Unless there are other questions from the audience, I would just thank Raudel once again for the nice talk, and thank you all for attending. We'll come back with another seminar next week. So thank you so much.
Okay, thank you so much.
Bye.